Since the day you were born, or actually even earlier, until the day you die, one part of you works hard to keep you going. It's your heart. But it's not just you. The whole universe ticks, the planet ticks, we all tick in one way or another. And as everything in this universe ticks in some way, so do games. In today's episode, we'll be talking about what makes the games tick. So stay tuned. How does a game become alive? What makes the game fluid and interactable? Humans perceive movement as a continuous process. Everything around us moves with a logical continuity. Objects can move fast, move slow, they can move at constant or varying speed. Humans discovered quite some time ago that the human eye can be deceived to perceive continuous movement by watching discrete moments that exchange fast enough. Simple as that. This brought us to the first films in the 1890s, a real revolution. We also realized that if we catch more of these discrete moments in the same amount of time, the movement will look more natural and fluid. Movies with higher frame rates were born then. But how does this apply to games exactly? If we think of a game as a movie, by eliminating the interactable part, obviously, it's basically the same thing. It shows a set of pictures in an amount of time, which gives us the perception of objects moving and interacting on screen. The more pictures per second you see, the more real it looks, the more fluid it looks, right? Same as movies used to show 24 pictures per second using projection technology, the games use the update loop to keep it spinning and updating a certain amount of times per second. However, this doesn't necessarily mean that that's the frame rate you get. What is the update loop? Well, the update loop is a loop that spins from the moment you start your game until you shut it down. To dumb it down even more, it could be as simple as an infinite while loop that keeps repeating the same operations every time it loops. The operations it does are getting the user input, updating the game state, and drawing or rendering the game. This loop is the heart of the game. While it's looping, it's keeping the game alive and happy. The only reason why I feel the games are alive and interactable is because the game checks what you did, updates the game state, and draws everything on the screen faster than you can perceive. The amount of times a game performs these steps is what we call the game update frequency, which might or might not be the frame rate you get in the end. With no limitations set, the loop will spin as fast as your computer can run it. This is not a good idea generally. Just imagine that you have an object that's moving by a certain amount every update. The faster the loop, the faster the game. It will be impossible to play that game really. Now let's get back to the loop operations. I mentioned there's three of them. There is user input game state, which is also frequently called simulation, and game drawing, aka rendering. We can simplify it even more by dividing it into only two areas instead of three: simulation and rendering update. Okay, hope you're ready for the next part. Let's go. Simulation can in theory be spinning with a completely different frequency than rendering. This might sound confusing. Simulation entails all game state updates, like calculating where everything in the scene is. Rendering is the operation of drawing that state on the screen. But if we separate them, why would we separate them, right? Doesn't it make sense that every time we update the game state, we update the things on screen? We draw a different state. Let's first talk about three main approaches in setting up the game update loop to understand why we do this. So the first approach is frame rate or rendering frequency and game state updates coupled and dependent on constant game speed. That's a lot of words. In this approach, we can, for example, run our main update loop to run 30 times per second. So we hard coded to that number, which is the old console standard kind of. And simulation and rendering both run each update iteration. That means that whatever needs to happen in our game, for example, updating the game position or anything like that, will happen 30 times per second. Also, everything will be rendered 30 times per second. In this approach, you usually code the game so it pauses for a while within that update loop, and it spends just enough time pausing there to hit the frequency of 30 updates per second. If we do the simple math here, it means that we roughly spend 33 milliseconds every time we loop, pretty much. But what is the problem with this approach? There must be a problem, right? Well, firstly, your PC might not be fast enough to pull off 30 updates per second. Your game might just be too demanding. If that's the case, the rendering part will stutter. Although your GPU might be capable of rendering it faster, it's just locked to the threshold of 30 per second. Secondly, if your PC is fast enough and you're locking your game update to 30 updates per second, you're wasting a lot of time. You could potentially be rendering 144 frames per second with no issues, but you choose not to since you're locked to the simulation update. This solution is good only as a quick and dirty solution to make your game run when you start the project, right? It should not be the state you publish your game in. The second approach is making it run as fast as possible with simulation and rendering still coupled. This method simply does not constrain your update loop, so it keeps rendering paired with simulation, and basically the more FPS your hardware can produce, the more updates you will trigger. What are the problems with this approach? Well, if your hardware is slow, it will cause frame drops and fluctuations in your game or simulation update loop. Your game will stutter and the player experience will be, well, not as good as it should. If your hardware is fast, it should be fine, right? It's just spinning as fast as it can. Well, not really. In game development, we deal with so-called floating point numbers, which I will cover in one of my future videos. Those numbers are correct only up to a certain decimal. So each calculation you do while your game is running, a rounding error occurs. This error is small, but it's still significant. Let's imagine that your character is traveling in a straight line, and let's say that the character is supposed to travel 100 meters. Depending on our frame rate, the character will move more or less per frame. If the frame rate is high, the movement per frame will be smooth. If the frame rate is low, of course, the character will practically jump around each frame, so it will stutter, right? Now imagine again that we have this high frame rate, so it's moving only by a few millimeters per frame, for example. This might cause problem for us, as we deal with floating point numbers. These are precise only to a certain degree, as I said before, so that means that the mistake in our position calculation would get bigger with higher frame rate. This is why having a super high frame rate coupled with game simulation running at the same speed is not really a good option either. And the third approach is constant game speed with maximum FPS. Well, this is the most advanced solution, and this is how most AAA games are made. You have your game simulation update loop spinning with a certain frequency, and then you have your frame rate as high as possible running completely independently. The fact is, you don't really need to update input and game state 144 times per second or more. In theory, 30 times per second might just do the trick for those kinds of things. You, however, still want to have the game being rendered at 144 Hz so it looks fluent. But there is one big catch here. Some of you might have already realized, if we update the game state, for example, 30 times per second, what will be rendered 144 times a second if nothing in the game changes for most of those ticks or updates? Well, here we pull out one of our main tricks in games development, interpolation and prediction. So if you have your simulation update running 30 times per second and your rendering update running 144 times a second, that means that you will, in roughly 1/4 of cases, want to render the same thing that happened in the previous frame because nothing really changed since the last frame occurred. However, you know at which speed certain things in your scene are moving, so by using that speed, you can predict or interpolate between the current game state and the predicted next game state to render. You know how much time passes between each render frame and each simulation update, and using that you know how much a certain object might have moved between two render frames. This renders just a prediction of what the next game state might be and might not be, right? It might get completely wiped when the next simulation update kicks in with the real new positions. However, this happens on a scale so small, it's not noticeable by the naked human eye. This approach works fine on any machine that will be capable of spinning the main update loop the specified amount of times per second, and of course rendering the game at an acceptable frame rate. If you want to build a high quality game, this approach is the way to go. Now you know what a game update loop is, and you know that it's pretty simple, but it's also magical, because we're forecasting the future to enable higher frame rates. If you like the content I'm creating, please do leave a like and hit that subscribe button down below. If you have any questions or feedback, please leave a comment and I'll try to answer. Enjoy and see you in the next one.